Okay, so section 2, we're going to talk about the 4 kinds of reactions. Synthesis, what do you know about, what's synthesis mean? Make something. That's going to be useful. Combustion means to what? Burn, explode. Decompose means to break down. Replace means switch or do something different. In this, it's replacement reactions. Why it has replacement, I don't know. So we're going to look at the different kinds of reactions. How are they classified? What are the characteristics? Here's your vocab. That's on the last slide, and most of it is just your types of reactions. So, chemists classify reactions in order to organize the different ways that things happen. So the very first type is a synthesis reaction. Synthesis, you said, means to make or to put together. So a synthesis reaction is when you have 2 or more reactants that are put together to make a single product. So in a synthesis reaction, I'm taking pieces and I'm putting them together. So I'm taking parts and I typically am going to end up with one product. So notice here I have 2 things, but it's 2 of the same thing. So I'm taking an element and I'm making one big component out of that. So synthesis, take pieces and put together into one. I'm going to look for one product. Combustion is actually, can be a type of synthesis reaction. Here again, notice I have 2 pieces and I have 1 reactant. However, oxygen has to be part of combustion. So I am going to look for oxygen as a reactant if I'm going to have combustion. And I think most of you know, in order to burn, fire needs what? Oxygen. So it has to have oxygen. So here, heated hydrogen reacts with oxygen. It produces heat and water. And this is, notice it's also a synthesis reaction. I do want to point out something else. Quite often when we talk about combustion and burning, you are going to have a hydrocarbon and oxygen, and you are going to produce CO2 and water. So this would also be a combustion reaction. Here again, you're looking for oxygen as a reactant, and it's going to produce carbon dioxide and water. I will tell you right now, if I look at hydrogen and oxygen makes water, and you labeled that as a synthesis reaction, I would not count that wrong, because it's a synthesis reaction and it's combustion. But if I have the second one, where I have oxygen and it produces carbon dioxide and water, you have to put combustion. That is not a synthesis reaction. So that would be your second type of reaction. Decomposition. Decomposition is simply the opposite of synthesis. Do I not have a picture for this one? Well, I guess I'll make one. A decomposition reaction then is the opposite of synthesis. So if I have water, which is a compound, I'm going to decompose it. I am going to break it into hydrogen and oxygen. So synthesis has one product. Decomposition has one reactant that's broken up into pieces. So decomposition vocab, single compound breaks into 2 or more. It might break into 3 pieces instead of just 2. And it often requires energy to break it. So water is often decomposed by adding electricity to it. If I put electricity through water, I can get hydrogen and oxygen. But I need some type of energy to break the bond so that I can break it into pieces. Then I have replacement reactions, and there's 2 types of replacement. Also, some books call it displacement instead of replacement, and I use both. They're both actually very common, so one day you might hear me say single replacement, and 2 seconds later I might say single displacement. It's the same thing. So it's a reaction when one element replaces the atom of another element. So if I look here, my A and my B are simply going to switch places. And in a single replacement reaction, I am going to have an element, which is why I have A, and a compound, which is why I have BX. So if I had an example, I could have sodium, 1 capital letter, it's an element. Oftentimes it's also a metal. And it's going to react with hydrochloric acid. So if my A and my B switch places, what's going to be by itself on the other side? H. And what do I know about H when it's by itself? H2. It's a gas. So it's going to produce H2. And then my sodium is going to go with what? Cl. So NaCl plus 1 minus 1, so I do not need subscripts. So that would be an actual example of single replacement. Element, compound, element, compound. And I could have put NaCl and H2. It totally does not matter which order that goes in. So a single replacement has an element and a compound. The element and the cation switch places. That's single. So double, if I'm not going to go to double yet. I'm going to stick with single reactions. And there is a reactivity series, is what that's called. Some metals are not reactive enough to replace other metals. So if I look over here, this is the most reactive, this is the least reactive of my metals. And then if I look at halogens, this is my most reactive, this is my least reactive. So if I'm looking at this table, if I had, let's pick something, I have Ag plus LiCl. Where is silver at? On the bottom. Here's silver. Where's lithium at? Towards the top. Silver is not this would not happen. Silver is not reactive enough. It doesn't have enough energy. It cannot replace that. That reaction will not happen. It can't occur. So if I did want to, can I replace lithium with anything on there? No, because lithium is the most reactive. If I want silver to replace something, what are my 2 options here? Platinum or gold. So if I have platinum, then that will actually happen. So with the activity series, some elements are not active enough or reactive enough to switch places with the other one. I do not expect you to memorize that table, but I expect you to know how to use that table. So will this replace that? Will this reaction take place? And the only time you use the activity series is in a single replacement reaction, because it's usually a metal or a halogen that's doing the replacement. I'll save those for at the end. I'll finish the lecture first. So, the other one is double replacement reactions. So, a double replacement occurs when I have ions exchange between two compounds. So, notice now, instead of element compound, I've got compound, 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 compound. And here again, I like to use the fronts. So if I were to draw this, I would have CaOH2 and HCl and produces CaCl2 and 2H2O. Here again, I think I told you guys last time, if I have an OH in my reaction, I am going to write my water as HOH. Did I tell you guys that? No. Okay, I'm going to tell you that now. Water is H2O, so 2 hydrogen and an oxygen. If I have a hydroxide in my reaction, quite often I write water as HOH because it just makes things easier. So if I look at this, I still look at my cation ions. So my calcium and my hydrogen are going to switch places. The easy way to say it is the fronts switch. So my calcium now ends up with chlorine, and my hydrogen ends up with my hydroxide. And that's how I get water. So if you want to look at this in the book, that's totally fine, but to me it's easier to think that the front, the cations, are what switch places. And then often in double displacement, that's when we're going to get a precipitate, which is that solid, and we did the example with the iron chloride the other day. So when I take two liquids and pour them together, and I get that chunky solid, that's a precipitate. And they are very common in double replacement reactions. And then all double replacement reactions should produce either water, a precipitate, or some type of gas. And we'll use those in the lab on Monday. We've seen precipitates, and we're going to do that in the lab, so I'm not going to actually show that animation. Table, this just kind of gives you an idea, and it's kind of what I've told you before. So write your components. Step 1, write the symbols. Step 2, balance your charges. And step 3, you're going to balance the entire equation. This breaks it up into more steps, which you can definitely look at that. But I think if you follow my 3 steps, it works just as easily. But this table I do like, and this is an interactive table that's on your LearnSmart or on your computer. But there is a table in your book, like 297, 298, somewhere in that area, that has the generic equations for each type of reaction. And that's a good table to look at. And that's what I have for types of reactions.